It came in the same plane as the planets around the Sun. It will come very close to Mars on October 3rd to get a high-resolution image of it from the Mars Reconnaissance Orbiter that was deployed by NASA.
An interstellar object is racing toward the inner planets at a speed faster than any spacecraft humans have ever launched. Its orbit is bending closer to Mars, and Harvard's Avi Loeb, along with scientists at NASA, now warn that 3I/ATLAS might not simply pass by Mars. It could collide with it. New evidence suggests that large explosions are already happening in the universe. Could this be the first evidence of alien technology or the setup for the next planetary disaster? Today, let's break down the flyby that turned into a warning.
The largest telescope ever flown launched into deep space some captivating images as Webb peers back toward the origin.
Harvard astrophysicist Avi Loeb has suggested the 3I Atlas is actually some type of alien technology.
When Comet 3I/ATLAS was first detected by telescopes in mid-2025, the story looked simple. Astronomers using the Atlas Survey Telescope picked up a faint blur moving rapidly against the background stars. Its trajectory showed it wasn't local. This was an interstellar object, the third ever discovered after Oumuamua in 2017 and Borisov in 2019. Excitement spread quickly. For the first time, spacecraft orbiting Mars could capture an interstellar visitor up close. NASA's Jet Propulsion Laboratory created early orbital models. These initial numbers showed a safe path, with the comet swinging through the solar system, passing near Mars in late September 2025, then curving around the Sun before heading back into deep space. Astronomers were thrilled. Mars orbiters and rovers would be in perfect position to observe it. Science outlets compared it to earlier interstellar visitors, strange, but ultimately harmless. For weeks, the outlook was clear, a spectacle without danger. Then, new signs appeared. Observatories refining the orbit noticed small but consistent deviations, shifts too precise to dismiss as random noise. At first, astronomers thought more data would smooth them out. Instead, the irregularities grew. By late August, the differences were undeniable. Early September marked the turning point. Harvard astrophysicist Avi Loeb and his team released updated calculations, while independent groups at NASA's Jet Propulsion Laboratory ran their own. Both teams came to the same troubling conclusion. That raised a critical question. What are the chances NASA will acknowledge this fully? Because doing so would only deepen the doubts. 3I/ATLAS wasn't just drifting, it was adjusting. Loeb described the changes as fingerprints of control. Its path wasn't simply the result of gravity. It was fine-tuning itself, inching closer to Mars. The shifts were tiny, measured in fractions of an inch per second, but across tens of millions of miles, they made a major difference. They pulled the comet's track directly toward Mars's orbital lane. NASA's JPL confirmed the effect. Their new models showed the safe corridor shrinking. Instead of widening with time, as expected, the gap narrowed. Chaotic outgassing could push a comet, but never with this level of precision. The pattern looked intentional. Loeb, already known for suggesting Oumuamua might have been artificial, argued that 3I/ATLAS offered an even stronger case. Reach the planets, and it will continue along its course to the next star, and we just need to keep our eyes on the ball. Officials spoke only of non-gravitational accelerations without adding speculation. But leaked briefing notes showed a quiet shift in risk assessments. The chance of a Mars impact had grown. A collision was still unlikely, but it could no longer be ruled out. For planetary scientists, even a fraction of a percent was enough to sound alarms. Behind closed doors, the agreement between Harvard's team and NASA carried weight. This wasn't just one researcher. It was multiple groups analyzing separate datasets and reaching the same conclusion. That consensus triggered high-level meetings. Observatories worldwide pushed data into fast-track reviews. The Mars Reconnaissance Orbiter was ordered to prioritize monitoring the object. Meanwhile, public messaging stayed calm. Space agencies presented the event as a rare chance to study a traveler from another star. News outlets echoed the optimism. Outside of specialist circles, almost no one realized the flyby story was unraveling. For those tracking the numbers closely, the meaning was clear. 3I/ATLAS was no longer just a curiosity. It was steering closer to Mars, showing adjustments too precise to explain away, cutting through space at impossible speeds. If the trajectory was concerning, the speed made it extraordinary. This interstellar visitor isn't just fast. It's moving at a velocity beyond anything humanity has ever tracked inbound toward the Sun. Current measurements place it near 194,000 miles per hour relative to our star. To put that in perspective, it could travel the distance between Earth and the Moon, about 238,900 miles, in less than 80 minutes. By comparison, the fastest probes we've ever built, like Voyager or New Horizons, crawl at a fraction of that pace. None comes close to such relentless speed. That velocity brings serious consequences. At this pace, even the smallest nudge can create dramatic shifts. Astronomers describe it as the butterfly effect of celestial mechanics. A shift of micrometers per second here, multiplied across millions of miles, can push the object thousands of miles off track. That's why the corrections detected by Harvard and NASA are so important. They aren't minor blips. They're magnified by staggering momentum. And 3, I/ATLAS isn't moving in isolation. Along the way, it feels gravitational pulls from the Sun, from Jupiter, and especially from Mars. Each tug is small, but combined with its unstable course, they make the trajectory harder to predict with every update. Each recalculation shows the same troubling pattern. The margin of safety around Mars keeps shrinking. For planetary scientists, the real danger lies not just in impact risk, but in unpredictability. At nearly 194,000 miles per hour, there's almost no room for error. A tiny adjustment, natural or deliberate, can be magnified into a shift large enough to send 3 I/ATLAS into Mars's orbital lane. And the unsettling part is that the object seems to be making such adjustments itself. Its speed also adds another chilling factor. If 3 I/ATLAS struck Mars, the energy released would be multiplied by that velocity. The kinetic force of billions of tons hitting at tens of miles per second is almost beyond imagination. It wouldn't resemble the slow-motion asteroid impacts we often see in simulations. This would be sudden, violent, and catastrophic, powered by an object moving faster than any natural body we've ever observed. The math leaves no doubt. 3 I/ATLAS is not drifting lazily through the solar system. It is cutting across like a blade, and Mars is directly in its path. A coma that shouldn't exist. While its speed was already astonishing, what came next shook astronomers even more. A comet's coma is the glowing envelope of gas and dust that forms as it nears the Sun. Normally, the process is simple. Sunlight heats frozen ices, gases vent out, and a halo develops around the nucleus. But 3 I/ATLAS isn't following those rules. Data from NASA's Mars Reconnaissance Orbiter showed that its coma didn't just brighten gradually as expected. Instead, it doubled in brightness within weeks. Alongside this, instruments picked up sudden bursts of high-energy ultraviolet light, the type of emissions never seen in normal comet activity. In typical comets within our solar system, gas venting stabilizes as they approach the Sun. They brighten and release material, but the process levels out. With 3 I/ATLAS, the opposite trend appeared. Even stranger was its composition. Spectrographs recorded an outpouring of carbon dioxide at rates far beyond anything previously measured in comets. By all known physics, that much gas should have torn the nucleus apart, breaking it down like a fragile snowball. Yet 3 I/ATLAS stayed intact, resisting collapse and behaving as if the release was controlled. That's why planetary scientists began to describe it in unsettling terms. The coma looked less like random venting and more like directed exhaust. Observers noted that plumes didn't erupt at random. They came in pulses, almost like timed bursts. Instead of dispersing outward in chaos, the gas streams appeared to steer, lining up with the object's shifting trajectory toward Mars. When its orbit was mapped, the effect was clear. Each brightening, each ultraviolet spike, matched with subtle but measurable course changes. On paper, it looked less like an object reacting passively to solar heating, and more like one actively using its coma to maneuver. For researchers trained to expect disorder in comets, this precision was shocking. It left 2 possibilities, both extraordinary. Either 3 I/ATLAS represented a new, unknown class of interstellar comet, capable of physics never observed before. Or it was deliberately engineered, a machine wrapped in ice, using gas jets as thrusters to guide its path. By the time these reports appeared in peer-reviewed journals, the object was already on course for its September encounter with Mars. And with every ultraviolet flare, astronomers faced a sobering reality. The closer 3 I/ATLAS came, the more it acted like a guided craft rather than a drifting comet. The 17-minute countdown. As if the accelerating coma wasn't strange enough, another discovery pushed 3 I/ATLAS even deeper into mystery. Its rhythm. Using the Gemini South Telescope in Chile, astronomers recorded something no comet in history had ever shown. The gas didn't vent chaotically. It pulsed exactly every 17 minutes. Observers logged the data for days, expecting the pattern to falter. But it never did. Pulse after pulse came with clockwork accuracy. Bursts of gas shot outward with machine-like precision. Normal comets don't behave this way. When sunlight strikes icy pockets, jets erupt randomly and unevenly, shaped by fractures and surface heating. Yet here was 3 I/ATLAS, supposedly a comet from another star system, firing bursts like an engine keeping perfect time. The implications shook scientists. A rhythm this exact didn't just suggest order. It suggested intent. Each 17-minute plume acted like a micro-thrust, pushing the object's trajectory ever so slightly. When these nudges were mapped against its orbit, they aligned with the very course adjustments, steering 3 I/ATLAS closer to Mars's orbital plane. For engineers, the comparison was impossible to ignore. It resembled the operation of spacecraft attitude thrusters, the small jets used to control direction. The pulses weren't venting gas into space at random. They were delivering thrust in deliberate directions, like controlled course corrections. The longer the pattern continued, the harder it became to dismiss as coincidence. Across multiple observation nights, the pulses remained perfectly in sync, timed like a metronome. The odds of a natural process producing such precision grew vanishingly small with each new data set. Even more unsettling was the math. Each gas burst, though tiny, generated just enough force to gradually close the gap between 3 I/ATLAS and Mars's orbit. Alone, the thrust was minor, but over weeks it accumulated. This wasn't a comet drifting by chance. It was steering. By mid-September, calculations showed that if the rhythm held, the object could shrink its missed distance from millions of miles to under 50,000, closer than the orbit of Mars's own moons. With just one stronger outburst at the right moment, its path could shift fully into collision. For the first time, many in the field voiced what once seemed unthinkable. This was not a comet, it was acting like a vehicle, and Mars appeared to be its destination. The Mars collision window. By mid-September, discussion around 3E/A TLAS narrowed to one phrase: the Mars collision window. For weeks, scientists had tracked its 17-minute pulses, each one working like a maneuvering jet. Feeding those adjustments into orbital models left no room for doubt. The object wasn't simply passing by. It was threading its way closer and closer into Mars's path. Official estimates placed its closest approach at 1.2 million miles on September 26, 2025. In cosmic terms, that margin is a razor's edge. For comparison, Earth's moon orbits just 238,900 miles away, while Mars itself spans about 4,200 miles in diameter. A pass within a million miles might sound safe on paper, but to planetary scientists, it's alarmingly close. At that distance, Mars' gravity isn't a background effect anymore. It becomes strong enough to pull on the object, changing its path in ways that could alter its future. And this is where the danger lies. 3I/ATLAS is already unstable. Every 17-minute plume nudges it slightly sideways. Each gravitational pull from the Sun, Jupiter, and now Mars stacks on top of those adjustments. The closer it comes, the more those forces combine. What began as a routine flyby has narrowed into a thin probability corridor where even the smallest push could flip the outcome. Calculations published in early September made the risk clear. If 3I/ATLAS gained just 6 miles per second of extra velocity, its orbit could swing directly into Mars. In interstellar terms, that's a very small number. A single powerful outburst from the comet's core, or a deliberate push, if artificial, could make it happen. That's why the period between September 19th and September 30th is considered critical. During these days, the object aligns almost perfectly with Mars' orbital plane. Any shift, no matter how minor, could lock it into a collision course. And if the 17-minute eruptions continue, by September 19th, the projected missed distance could shrink from more than 1 million miles to less than 30,000 miles. That's actually closer than Deimos, Mars' outermost moon. For space agencies, the stakes could not be higher. Dozens of active missions orbit and operate on Mars: the Perseverance rover, the Curiosity rover, the Mars Reconnaissance Orbiter, the ExoMars Trace Gas Orbiter, and others. These spacecraft act as relays, climate observers, and mapping platforms. A near miss could flood Mars' orbit with debris. A direct impact could wipe out years of exploration in a single moment, and it's not just about the hardware. For planetary defense teams, this is a real-world stress test. Humanity has simulated asteroid impact scenarios for decades, but never faced an interstellar object moving at such speed. There's no precedent and no established playbook. As September progresses, the possibility of impact hangs heavier. Whether 3I/ATLAS skims by or collides outright, one fact is certain: Mars is approaching its closest brush with cosmic fate in billions of years. What happens if it hits? The thought of a close pass is unsettling enough, but what if 3I/ATLAS actually collides with Mars? The answer is staggering. Based on radar data and brightness readings, scientists estimate its mass at nearly 10 billion tons, with a dense metallic core about 1,300 feet across, buried under its icy shell. Traveling at nearly 194,000 miles per hour, the energy of impact would be off the charts. Astronomers have calculated that a direct strike would unleash the equivalent of 2 million megatons of TNT. For perspective, that's thousands of times more powerful than the strongest nuclear device ever detonated on Earth. The explosion wouldn't just leave a mark, it would reshape part of the planet. Models suggest the crater could stretch 37 miles across and plunge more than 3 miles deep. For comparison, that's wider than the entire Los Angeles metropolitan area and deeper in places than the Grand Canyon. The strike would vaporize cubic miles of Martian rock, throwing debris high above the thin atmosphere. Some of it would fall back as a choking blanket of dust, while the rest would be ejected into orbit or launched into interplanetary space. The consequences for Mars exploration would be immediate. The Perseverance and Curiosity rovers could be hit by debris or buried in fallout, depending on the impact site. Orbiters like the Mars Reconnaissance Orbiter and Europe's Trace Gas Orbiter could be struck by lethal fragments, crippling the relay networks that connect Earth to the surface. Decades of exploration could be erased in a single day. But the destruction wouldn't stop there. A strike of that scale would likely change Mars' climate temporarily. Mars already experiences global dust storms that can last for months. An explosion of this magnitude could darken the atmosphere for years, ending any chance of solar-powered missions surviving. Instruments searching for signs of life, past or present, could be wiped out or disabled just as the planet itself becomes engulfed in its own dust storm. Then comes the broader risk to the solar system. Fragments blasted into space could escape Mars' gravity and spread outward. Some might enter paths through the inner solar system, meaning debris, possibly infused with material from 3A/ATLAS, could cross Earth's orbital neighborhood within decades. For planetary defense specialists, that scenario is almost as concerning as the initial impact. A collision on Mars would not just endanger one planet's exploration program, it could disrupt the balance of the entire inner solar system, scattering fragments, evidence, and potential threats across multiple worlds. Explosion in the universe. Astronomers have reported the discovery of an unusual and extremely powerful gamma-ray explosion that occurred outside our galaxy. The event was first detected in July and quickly drew international attention because of its unique behavior. Gamma-ray bursts are normally short-lived flashes of high-energy radiation, lasting from mere milliseconds to a few minutes and, in rare cases, a few hours. They are usually linked to catastrophic events such as collapsing stars or the violent pull of black holes. What made this case so striking is that the burst repeated multiple times over the course of a full day, something never seen before. The explosion was captured by several observatories, including Hubble and the European Southern Observatory's Very Large Telescope in Chile. Images showed a glowing orange point that pulsed repeatedly, confirming the source was not within the Milky Way, but in a distant galaxy. According to researchers, this pattern of repetition challenges everything previously understood about gamma-ray bursts. Antonio Martin Carrillo, an astronomer at University College Dublin and co-lead author of a study on the event, called it unlike any other seen in 50 years of GRB observations. He emphasized that gamma-ray bursts are not expected to recur because the processes that generate them are usually final and destructive. The strange gamma-ray explosions observed outside our galaxy have raised new questions, and one possible link scientists are exploring is with 3I Atlas. Objects like this move at incredible speeds and follow unusual trajectories, which makes them very different from the comets or asteroids we are used to seeing. Because 3I Atlas came from another star system, researchers believe it might carry clues about violent events happening in distant galaxies, possibly including gamma-ray bursts. Some astronomers suggest that interstellar objects like 3I ATLAS could be fragments ejected from explosive cosmic events such as collapsing stars or interactions with black holes. If this is true, the same kind of processes that produce gamma-ray bursts might also send solid material flying across the universe. When such material passes close to Earth, as 3I ATLAS did, it gives scientists a rare opportunity to study not only the object itself, but also the forces that launched it. The repeating gamma ray burst detected recently has made researchers wonder whether objects like 3 IATLAS could be physical evidence of the same violent processes playing out in other galaxies. Thanks for watching. Which part stood out to you the most? Share your thoughts in the comments. We always enjoy hearing.